Hi everyone, my name is Michelle Zhang, and today I will present my project on AI-based dynamic risk prediction after pediatric leukemia transplantation. The clinical setting is allogeneic hematopoietic cell transplantation, or allo-HCT. This treatment can be curative for children with high-risk leukemia, but the early post-transplant period is also medically fragile. The question is simple. Can we use information already collected in the electronic health record to update a patient's short-term risk in real time? The goal is not to replace clinical judgment. It is to build a decision support tool that may help clinicians recognize subtle warning patterns earlier. Allo-HCT can rebuild a patient's blood and immune system after intensive therapy, but patients can also experience serious complications, including death, acute graft-versus-host disease, organ toxicities such as veno-occlusive disease, and severe infections. The first 100 days after transplant are especially important because a patient's condition can change quickly. A lab value may look acceptable today, but become concerning a few days later, not only because of its absolute value, but because of how fast it is changing. Traditional risk models often use static information, such as demographics, donor match, baseline characteristics, and labs at one time point. Those variables are useful, but they do not fully capture physiology that is evolving daily. So the motivation for this project is that early post-transplant risk is dynamic. To model it well, we need to consider trajectories, including biomarker velocity and acceleration. This project asks two main questions. First, how can we integrate high-frequency, irregularly sampled EHR data into real-time clinical decision-making? In hospital data, measurements are not collected perfectly every day, and missingness can be clinically informative. Second, can we develop a framework that continuously updates risk for each individual patient as new data arrive? In this talk, dynamic means that risk is not one fixed number at transplant. Instead, risk can change after each new visit or lab measurement. So I used a retrospective cohort of 614 pediatric patients treated between 2000 and 2020. The data set includes about 46 longitudinal biomarkers measured over the first 100 days after transplant, plus baseline characteristics such as sex, race, and donor match quality. The main endpoint in this presentation is early post-transplant mortality. In the 100-day baseline summary, there were 36 deaths, or about 5.9% of the cohort. In the event file construction used for modeling, there were 37 observed deaths overall, because event records extend slightly beyond the 100-day biomarker window. This low event rate is clinically encouraging, but challenging for modeling. The model has to learn mortality-associated patterns from few events while avoiding overfitting. For that reason, the results are promising but preliminary. A future clinical tool would need more data, external validation, and calibration. So this model uses a recurrent neural network with a survival model. The recurrent part is a gated recurrent unit, or a GRU. A GRU is designed for sequence data. It reads patients' clinical history step by step, so that each new visit is interpreted in the context of earlier visits. That matters because the question here is not only what is the lab value today? It is also how did the patient get here? And is the trajectory becoming unstable? The survival part is a Weibull model. Instead of only classifying patients as high or low risk, the model estimates a continuous probability of an event over a future horizon, such as the next 30 days. At each visit, the model uses the history so far to estimate an updated 30-day mortality risk. Although this presentation focuses on mortality, the framework can extend to competing risks, where several possible events are evaluated together. A key part of this project is how missing data is handled. In many datasets, missingness is a nuance. In hospital data, however, it can be very informative. If a patient is unstable, clinicians may order labs more frequently. If a patient is stable, some labs may be checked less often. For each biomarker, the model receives the value, a binary mask indicating whether the value was actually observed, and the time since that biomarker was last measured. It also receives the absolute time since transplant and the gap between visits. This allows the model to distinguish between a recently measured normal value and a filled-in value that has not been checked recently. Clinically, these are two different situations. The model was evaluated with an internal 80% training and 20% validation split, stratified by event status. Despite the low mortality rate, the model showed promising discrimination. The validation analysis gave an AUC of approximately 0.8 for distinguishing patients who died from those who were censored or survived. Another way to view the results is through the predicted 30-day mortality risk at the final visit. The average predicted risk was about 0.236 among censored or surviving patients, compared with about 0.358 among patients who died. The key point is that the model assigns a higher risk on average to patients who later experience mortality. However, the validation set contains only about 7 death events. These results support the idea that dynamic biomarkers carry signal, but do not prove the tool is ready for clinical deployment. To understand what the model was learning, I used permutation importance. The idea is to shuffle one biomarker at a time across validation patients and measure how much performance worsens. If performance drops, that biomarker was important for prediction. The top biomarkers were AST, LDH, ALT, bilirubin, and BUN. AST and ALT relate to liver injury. Bilirubin reflects liver and bile processing function. BUN can reflect kidney and metabolic stress, and LDH is a marker of tissue injury and systemic inflammation. The manuscript also includes a classical univariate survival screen. That simpler analysis overlaps with the GRU model on markers such as LDH and ALT, which makes the dynamic model signal more biologically plausible. So this slide shows why dynamic modeling matters. The figure compares biomarker trajectories and their derivatives between patients who survived and patients who died. A first derivative represents rate of change, or velocity, and a second derivative represents acceleration, meaning whether the rate of change itself is increasing or decreasing. In the survival group, trajectories cluster closer to a stable region. In the mortality group, trajectories are more volatile, with larger movement in high velocity and high acceleration regions. This matters because two patients can have a similar lab value today, but very different trajectories. One may be very stable, while the other may be deteriorating quickly. The model can use that temporal pattern instead of relying on only one single measurement. So, The main conclusion is that this approach can shift monitoring from reactive to proactive. A reactive model waits until a patient crosses a clear clinical threshold, but a dynamic model may identify concerning trajectories earlier as biomarkers begin moving in a risky direction. This workflow is also scalable because it uses routinely collected EHR biomarker data and could update risk each day during the high-risk post-transplant window. The biological interpretation is encouraging as well. Important markers include hepatic, renal, and tissue injury signals, which align with clinical intuition about systemic toxicity after allo-HCT. The next step is to extend beyond mortality alone. Ongoing work applies this model to competing risk settings for acute graft versus host disease, veno-occlusive disease, and infections. And these are my references, and thank you so much for listening.